So let's start today's class. So this is the 5th session. So in the earlier weeks, we motivated the objective behind the course, that is Introduction to the Process Dynamics and Control. Then we studied about first order dynamical systems that were represented by a common transfer function of Gs equal to Kp upon tau s plus 1. Then we studied second order transfer function, and they were represented by Gs equal to Kp upon tau square s square plus 2 zeta tau s plus 1. And corresponding to these two first order, second order and higher order systems, we studied different kind of inputs, that is step input, ramp input, sinusoidal input, and using these inputs and this transfer function model, we studied the responses. And once we have the responses of any given system, we then moved on to the control philosophy. So what kind of control we can implement. So we studied about feed forward, feed backward, and control objectives such as servo problem, regulatory problem. And in the last class, we were studying about this feedback control, then block diagram representation. Then we studied different kind of controller, that is PI, PID controller, and then we solved few of the numericals related to that. And in today's class, we will be solving few of the questions related to this block diagram representation, and then we will solve few of the questions related to stability analysis using let's say roots array. Then the other is direct substitution, that is we can straight away put s equal to j omega. Then other is using Bode criteria. Apart from this, there are some other criteria also from Nyquist plot that we can look on another class. So today we'll just solve numericals related to the block diagram representation step and stability analysis using that by using these two criteria. So first we will just study what are these two stability analysis and why do we need them individually. So in today's class we will be studying about the stability analysis. Okay, so let us just revise what we studied in earlier class, last class. So in the last class and also in the classes before that, we studied about this block diagram representation that is essentially represented by this four main transfer function or four main block. So first of all, we give a set point to the process, that is YSP, and then we will be having some measurement from the plant, that is YM, and our aim would be to manipulate, to find the input such that we can track this set point. So basically we want to minimize the error between the set point and the measurement. That is why we calculate the error, and then this error is fed to controller. So what controller will do is, based on this error and the kind of controller we are having, it will generate a control action. And let's say if the transfer function of controller we usually represent by GC, that control action will be fed to final control element. So that is basically control valve, or if we are having on-off system, then it will be an on-off valve. So basically here we will be having a final control element that is represented by GB. So this final control element will give the physical manipulated input. So it will convert the control input into the physical signal. So that will be ultimately provided to the process. So over here it will convert the control action into input, and that will be provided to the process, that is GP. And from this process we will be getting the measurements or the output, and ultimately we are feeding this back measurement. So this measurement we will be getting from a sensor. So corresponding to that sensor or the measuring device, we will be having another transfer function block, that is GM. So this will complete our closed loop. This will complete our closed loop, and we might be having some disturbances to the process, and if the disturbance is represented by transfer function model of GD, then we can add this block over here. This will be a disturbance. So if I want to write the transfer function between the output and the set point of this block diagram, so we can simply write it using y upon ysp. Then over here we will be having the open loop transfer function. That is, if we were not having this feedback loop, then what would be my transfer function have been? So that would simply be multiplication of each of these three blocks present in this open loop. That is basically GC, GB, GP, and then upon the closed loop transfer function. So ultimately it will become 1 plus the product of each of these three transfer function block. So this is just a simple way to remember the transfer function. So this entire is known as transfer function of this block diagram representation, and the denominator is called as characteristic equation. So to study the stability of any process, we will be requiring this characteristic equation. So we will be analyzing this characteristic equation, and on the basis of that we will be commenting on the stability. So over here we can see a controller block. So corresponding to that we studied different kind of controllers. For example, we studied this different kind of control actions such as proportional control, integral control, derivative control, and PID control. So the first one we studied was proportional control, in which the control action taken was directly proportional to the error. So and then we obtained the transfer function model for the controller. That is this thing. That is, the control action will be proportional to the error, and ultimately the transfer function will become P of s upon E of s is equal to Kc. And this is known as controller gain. Controller gain for proportional controller Kc. Similarly, we know that in case of proportional controller, we won't be able to achieve the set point, that is perfect control won't be possible. There will always be an offset of some fixed value. That is why proportional controller itself is not used unless we can tolerate certain amount of offset. So in order to mitigate this offset, what we do is we use an integral controller. So in proportional controller, the control action is only proportional to the current error. Whereas in case of integral control, what we do is we also take into account the past errors. That is, from 0 to t, all those integral error we will be accounting. Similarly, in case of derivative control, we won't be looking into the past, but we will be looking into the rate of change of error. So in future, how will my error change? So that is basically represented by derivative with respect to time. So integral control will be characterized by d by dt. So the derivative controller will be characterized by d by dt. Integral controller is due to this integral into past, and proportional control is simply proportional to the present error. So using that, we just derived these control laws. So corresponding to each of those things, we had these transfer function models. And then in industry, most commonly used controller is this PID controller, whereby we use each of those control action, that is proportional, integral, and derivative. And then we studied that there are these parameters Kc, tau I, tau d. We can call it as control parameters or controller parameters that we need to tune such that the system is stable. So even though if we use the PID controller, if these parameters are not properly tuned, then a system can become unstable. So in order to know whether for the given system of controller parameters kc tau and t tau d, whether my system will be stable or not, that part we'll be studying today. So then we studied different kind of plots related to varying the controller. Then in PID controller we tried varying the values of kc, tau I, tau d, and then we studied the plots. Then we studied this on-off controller. So today we will be starting with this week 5, that is related to the stability analysis. So first we'll study what do we mean by stability of dynamical processes. So there are different kind of marginal stability, asymptotic stability, and basically unstable process. Then we will study this Laplace domain analysis. So over here we can just study the roots of the denominator and comment on the stability. So we already studied that if I plot the poles and the zeros, if my poles lies on the left half plane, that is on this plane, then I can say my system is stable. So we find the poles of the transfer function, that is basically in Laplace domain only. So basically g of s will be some kp upon tau square s square plus tau s plus 1. Then we will find the poles of the denominator in Laplace domain only. So that is what we mean by Laplace domain analysis. So over here we need to find the roots of the denominator in order to comment on the stability. But for higher order systems, finding the root can be slower or it will be difficult. So we then analyze this system using approaches whereby we don't need to find the roots of the system. So that one such approach is known as roots array. So over here also we'll be using the Laplace domain. So in these two we'll be just using the direct substitution and root array to analyze the stability. Then we will study that for the systems where we are having an exponential term over here, okay, exponential, let's say tau ds, then this conventional approaches related to root array won't be possible, because basically we need to find the root of this equation. So there are these approximation techniques whereby we can approximate this in using linear term, but that won't be, basically that are approximation techniques. So in the presence of this exponential term, how can we analyze the response of the system? So that we can do by converting the system into frequency response. So basically we just replace s equal to j omega, and then on the basis of the plots of omega we will come upon different kind of stability criteria, that is the Bode stability criteria. Then we will also study this. In this we will study about the gain margin, phase margin, gain crossover frequency, omega c phase crossover frequency, and using this we will comment on the stability. So these two chapters will cover that, frequency response and frequency domain analysis. So I'll just quickly cover through the basic concepts behind that. So first thing, let's just consider a simple case of liquid surge tank. If I'm having a tank whereby I don't have a control valve, or let's say on-off valve, and this F output is constant. Since the opening will be constant, the flow rate outside this will be constant for let's say if the height is constant. Now the input to the system, or let's say disturbance, the system is F input. Now if I keep on increasing the value of input to the system, the value of height will keep on constantly increasing, since the flow output is constant. That is, Basically, if I keep on increasing the input, the flow output will also keep on increasing. So we don't have the fixed value, or the output is not bounded over here. So in that case, we can say the system is unstable. However, what we can do is we can just employ or use a control valve or an on-off valve over here, such that we can control the output level. So using this control valve, initially what we can do is we can just control the level of the tank to some fixed value. So this is basically level of the tank, plot of the level. So basically my output will be bounded to some fixed value if I use the control valve. That is, using a control valve, what we are doing is we are converting an unstable system into the stable system. However, initially the steady state was this value, ys0, but after using the control valve, the steady state system might change. That is, we move from one steady state to another steady state. That is what it has been mentioned earlier. It settles to a new value of very close to the ultimate previous steady state value. Then there are these two kinds of stability. The first one is marginal stability and the second one is asymptotic stability. So over here it states that if the system is disturbed by a bounded input, like a step input, the response of the system is also bounded, then the system is stated to be marginally stable. So the key point over here is we are giving a bounded input, and if the output of the response is also bounded, then we can call it as marginally stable system. So let's say if we are having a process, and if I provide an input, step input, then corresponding to that, if I get the value of ys, so that it keeps on increasing, but ultimately it becomes constant to some fixed value, then we can say that it is marginally stable. It might happen that if the input is, let's say, sinusoidal or some kind of oscillatory input, then ys can also be, let's say, constant sinusoidal. But over here we can see that the maximum value as well as, let's say, the minimum value is bounded within this range. So even though the values are constantly keeping on changing, still the response is bounded. So we can say that this system is marginally stable, because for this bounded input we are getting a bounded output of the system. Then there is a stronger definition of stability, which says that if the input is bounded, the response is also bounded, and in addition, the system returns to an original steady state. So this is a stronger definition of stability because of the second criteria, that is, the system will respond to an original steady state. When I say original steady state, that means that, let's say, if my input is constant at some value of 10, and corresponding to that I am having my output which is fixed at some value of 0. Now at time t equal to 1, I provide a step input to the system, and that step input remains constant. So what will happen, as soon as I provide the step input, the response of the system will change. So let's say if it keeps on increasing, but we can use a controller and force the response to go back to the original state. That is, it can again, so this one was the original steady state, then using a controller we can force the system to ultimately reach this steady state. So it will reach its original steady state. So basically ys new, that is the new steady state, is equal to the old steady state. So such a kind of system is known as asymptotic stable system. So this is a stronger definition of stability. In case of marginal stability, it can reach a new steady state. So this will be our new steady state. So this is also a stable system, but it is only marginally stable since it is not returning to the original steady state. So as in earlier class we studied that just because we are using a controller, that doesn't mean that the system will be stable. It simply means that we can get the desired set point after a few amount of time if the controller parameters are properly tuned. So that is what it has been stated in the lecture notes, that is, feedback control can stabilize the unstable process then feedback control can convert the marginally stable process into a asymptotic stable process. Similarly, a feedback controller can destabilize a process. So in class we studied about this 3 CST are in series. So corresponding to that, if they are connected in series, then the transfer function would have been, let's say, kp1, kp2, kp3 upon tau1 s1 plus 1 plus whole cube. So this was the transfer function, and then if we use the PI controller, and then in the class we had, sir had shown that for different values of the controller parameters, this system can become unstable. That is, feedback control can also destabilize a stable process. That is what you had studied. So basically, stability condition limits the rangeability of controller parameters. So the parameters values are dependent on the range on which the system will be stable. So this system will only be stable for a certain range of these controller parameters. So that we can find it using stability analysis. So that is what I have mentioned over here, that in the example of CSTR, we said that feedback controller can, for a wrong value of controller parameters, it can destabilize the original system. That is, it is very important to know that what are the bounds of the controller parameters that we need to provide to the system. So this stability analysis can be done using Laplace domain or frequency domain analysis. Then all we are interested in terms of assessing the stability analysis by doing the stability analysis is to find the pole and see if the poles or any of the poles lie on the right half of the plane. So yes, when I say Laplace domain analysis, that only means that we want to analyze whether my poles are lying on the left half plane or not. If the poles are lying on the left half plane, that means we can say that the system is stable. And then there are approaches to find whether the poles are lying in left half plane or not, that we will study right now. So yes, right now we are studying the stability of the closed loop process and existing of a, so these 2 points are important. So this point is about the existence of positive pole leads to the instability of the process. That is, if the poles are on right half plane, then the system will be unstable. So in this, we need to calculate the poles of the system. That is, given the transfer function numerator upon denominator s, we will find the roots of the denominator that will give us the poles of the system. So we need to manually calculate the roots of the system. But for higher order system, if the calculation of roots becomes difficult, then we can use the root Hertzsprung criterion for stability. So what it does, what the advantage is that we don't need to calculate the actual values of closed loop poles. Rather, it calculates whether any pole is on left hand side of the imaginary axis of the complex plane. So without calculating the poles, we can find whether the poles are lying on the left half plane or right half plane. So in other words, we can say that Root's Hertzsprung criterion can find whether the closed loop transfer function is stable or not. And ultimately, using that, we will find the limiting conditions for the controller parameters, which would ensure the stability of the closed loop control system. So then there are the steps how we will analyze the root array. So the first one is we will find the characteristic equation of the polynomial. So the given the closed loop transfer function, the denominator will be the characteristic polynomial, and then we will write it in terms of the decreasing order of s, and we need to ensure that the first term, that is a0, should be positive. If a0 is negative, we can just simply multiply the polynomial with -1, and then we can analyze that if any of the coefficients, that is a0, if any of the coefficients, that is a1, a2, a3 is negative, then there exists at least one unstable pole in the closed loop system. That is, if any of this a1 to an is negative, then we can say that at least one pole lies in this half, that is, the system is unstable. So if we are having, let's say, s cubed plus s square minus s plus 1, if this is my characteristic equation, then we can see that one coefficient is negative over here. That means this system, wait a minute. So just give me a minute, I will connect again. Okay, so we are back. So yes, what you are studying is, we were studying this root array, and we were looking that if there is this presence of negative sign, then we can say that the system has at least has one pole in the right half of the plane, and consequently we can say that the system is unstable. Then if all the coefficients are positive, then we need to follow the following table called as a root array. So while we solve the numericals, we will take a deeper look into this array. And consecutively, we can also analyze the first column, that is A0, A1, A1, B1, C1, and comment that on the stability of system using these 3 points. That is, a system is stable if all the above elements in the first column of the root array are positive. That is, if all of these values are positive, that implies system is stable. Similarly, if any one of the element of the first column is negative, we have at least one pole on the right hand side of the imaginary axis, and the closed loop system is unstable. Then we are having the number of times the sign changes, that is from positive to negative and to positive again. This indicates the number of unstable poles present in the closed loop systems. That is, let's say if we are having s raised to 5 plus s raised to 4 minus of s cube plus s square minus of s plus some constant kc. So here we need to calculate the number of sign changes from positive to negative to positive again, and so on. So that will indicate the number of unstable poles present. So over here we are not having the sign change, but over here we are having the presence of sign change, that is this going from negative to positive. Similarly, over here also we are having sign change, it is going from negative to positive. So the presence of such sign changes can give us the idea about number of unstable poles present in the system. Then we will study this direct substitution. This is nothing but what we will do is first we will just substitute the value of s equal to I omega in the characteristic equation, and then we studied that if poles are lying on the left half plane, then the system will be stable. So using that we can find the control parameters using that simple criteria. So that is what we mean by direct substitution. That is, we need to plot the root locus, basically the roots on this complex real and imaginary plane. So let's start with solving the numericals related to this, and later on we will study the frequency response. So yes, these are the questions that we are going to solve today. So let's start with question number 1. So over here we have been given the block diagram of a system with a proportional controller is shown below. So over here we are having KC, that is corresponding to controller, then this is process. This you can call it as the transfer function model corresponding to the input. Then we have this measurement model. Then this R you can call it as set point, and this is, you can call it as the response of the system, and this is the input. So given this block diagram, we have been asked to find a unit step input. We have been asked that a unit step input is introduced in the set point, the value of Kc to provide a critically damped response for u equal to 0, tau p equal to 8, and tau m equal to 1 is dash. So over here we have to find this control parameter Kc such that the response is critically damped. So we, in the earlier class, we studied different kind of responses that is corresponding to zeta equal to 1, less than 1, greater than 1, and if zeta is less than 1, then we call it as, if zeta underdamped system, if zeta equal to 1, then we call it as critically damped system, and if zeta is greater than 1, then we call it as overdamped system. So using this block diagram, what we need to do is we need to write the transfer function of the form of n of s upon d of s, that is numerator upon denominator. Then since we are having this two transfer function in s domain, ultimately the denominator will be a second order equation, and then we will compare that transfer function model with the transfer function model of a second order system, that is kp upon tau square h square plus 2 zeta tau s plus 1, and using that we will calculate the we can compare the coefficients and then equate zeta equal to 1 and then find the value of Kc. So I will give you, let's say, 5-10 minutes to solve this question. So right now it is around 7:40. So we can try solving this question at 7:50. So within 10 minutes I will discuss the solution of this question. So I'm just pasting the question over here. Solved by 7:50 p.m. Meanwhile, if you have any doubt, you can ask me. So let's start with solving this question. So we have been given this block diagram. So first, what the first step is, we will write the transfer function. Now over here, we can write the transfer function between the output and the input. That is, we can write the transfer function between C by U as well as C upon R. But since we have been given that U equal to 0, the term corresponding to basically G of something into U plus G of something into R, so this term will automatically be 0. So we only need to find the transfer function, that is basically output C by R, that is C of S upon R of S we need to find. So what we will do is, so we need to consider this thing and this thing. So the first thing is, we will write the open loop transfer function, that is in the absence of this block. So that will be simply the product of these two transfer function, that is Kc into 1 upon tau Ps plus 1. And in denominator, we will be writing 1 plus closed loop transfer function, that is the product of each of these three blocks, that is Kc into 1 upon tau Ps plus 1 tau Ms plus 1. So now we need to simplify this, and we will find that this is a second order system. So in order to simplify this denominator will ultimately get cancelled out once we multiply it over here. So Kc upon tau Ps plus 1 tau Ms plus 1 plus Kc. Then we can open this bracket and simplify it further to get Kc upon tau P tau M S square plus tau P plus tau M S plus 1 plus Kc. So this is what we will be getting. So if I just write it over here, so transfer function becomes Kc upon tau P tau M S square plus tau P tau M S plus 1 plus Kc. Then we can replace the values that you have been provided in the question, that is tau P is 8, tau M is 1, and the value of Kc we have to find. It is Kc, tau P and tau M, tau P was 8, so 8 into 1 is 1, so this becomes 8s square plus 8 plus 1, that becomes 9s plus 1 plus Kc. So this ultimately we will be comparing with Kp upon tau square S square plus 2 zeta tau S plus 1. So this, both of this equation we need to compare. So for that we need to see that the last term should be 1. That is why we need to eliminate this value of Kc. So what we will do is, we will just replace this entire thing by 1 upon Kc, so that we only have these three terms whereby the last term is 1. So that is, it will become, I can take 1 upon Kc common, Kc upon 1 upon Kc upon, it will become 8 upon 1 upon kc whole s square plus 9 into 1 plus kc plus 1. So now we can compare the denominator of both of this equation easily. That is 8 upon 1 plus kc is equal to tau square, and then 2 tau zeta is equal to 9 upon 1 plus kc. I hope I have done everything correct. So once we have this, we need to find the value of kc for a critically damped system. So in the question we have been given that for a critically damped system. So that is why we can replace the value of zeta as 1. So that will give us the value of tau as 9 upon 2 1 plus kc. So this value of time constant we will put it in this equation to find the value of kc. So it will give us 8 into 1 upon kc is equal to, am I audible? Okay. So it will give us 81 upon 2 whole square, that is 4, 1 plus kc whole square. That is 1 plus kc is equal to 81 by 4 into 8. Am I correct? So yes. So this will ultimately give us the value of kc as 81 by 32 minus 1. So that we can calculate. by 32 minus 1. So this is 1.531. So this is the value of controller parameter, that is proportional controller gain, that is kc we found out. So just to analyze what we did in question. So we found out the value of the proportional controller constant for critically damped system. That is, for the value of kc equal to 1.531, the system is critically damped. That is, the response won't be oscillatory, it will be such that. However, if the value of the controller changes from this value, if that's either decreases or increases, then the system will become underdamped or overdamped, and correspond, if it is underdamped system, then maybe we can see the oscillations, or if it is overdamped system, then the response will become more sluggish. So that is the importance of finding the value of controller parameters kc. So it can change the nature of the response. So that was the purpose of solving this question. So next we will solve another question. So yes, the final answer of this question was 1.531. So that was option C. That is option C. Now the next question. So over here we won't be solving this question. I'll just go take you through the walkthrough or the methodology behind this question. So in this question we have been given the block diagram for a process with feedback control for output deviation variable h is shown in the figure below. All transfer functions are given with the prefactor s in minutes. A unit step change is made in the set point at time t equal to 0. So over here we are providing a unit step change. The time required for h to reach the 50% of its ultimate value. So ultimately this will become 50% of its ultimate value, that is steady state value, and corresponding to that we have to find the time. So how can we do that? So again, in any of this process, first we need to find the composite transfer function of this system, and then we can take So this transfer function will be of the order of form of h of s upon set point, basically this h bar s upon h sps. Then we need to take Laplace inverse of this transfer function. That will give us h of t with some value of this. Over here we'll be putting the value of this as 0.5 of steady state value, and corresponding to that we can find the time. So first, once we have this transfer function model, we need to find the steady state value also. That is basically the ultimate value, or we can also say final value, and we can calculate that using final value theorem. So that is limit t tends to infinity, s fs or ys can be calculated as limit s tends to 0, s ys. So using this we will be getting the ultimate value, that is ISS. So as in the solution, we can write the transfer function model of the open loop function as the product of these three terms, and in the denominator it will be transfer function of the product of the entire loop. So that is given by this equation, and then we can simplify it, and we can see that this term, so basically these two terms will get cancelled out. That is why we only have this first order transfer function model, that is given by 2/15 upon s plus some constant over here. So this is a first order transfer function model. Then we find the inverse of this system, so to basically convert into time domain. So for that we convert it into partial fraction method, and then we have this equation with respect to time. So in order to find the ultimate value, we can put time t equal to infinity, or we can put s equal to 0 in this equation also. That is basically I will be multiplying this by s, and then I need to put the value of s equal to 0, so that can also be done. That is ultimately it will become, this is my transfer function 2/15 s plus 0.8, then corresponding to this step input we will be having 1 by s. So this is my y of s. Now final value theorem states that s y of s tends to 0. That is I will multiply it by s and then put s tends to 0. So these two terms s will get cancelled out, and we will have 2/15 into 0.8. So 15 8s are 120. So this will become 2/12. That is 1/6. So it's the ultimate value. We can find it using the final value theorem. It will be 1/6, or we can use the conventional approach whereby we put the value of t equal to infinity. So over here also we are getting the ultimate value as 1/6. So that value 1/6, that is the final value. We will be, and we have been asked to find the time corresponding to the 50% of the ultimate value. That is yt will be half of 1/6, that is 1/12. And then we have this value 1/6, that is kp 1/6 coming over from here, and then we have this time transient. So over here we can just solve this and find the value of t, and we will be getting it around 0.867. Since this prefactor was in minutes, this also we can say in minutes. So that is our final answer, 0.867 minutes. Now this is a very similar question to the previous one. So in the previous question we were given the response value, and then we had to find the time taken to find the given response. Whereas in this case for the given block diagram, we have to find a change in the response value when a unit step change is provided. So that is, we have been given this transfer function, and then we have to find the response. However, in this case, the transfer function model, the process model, we are given as second order system, whereas in earlier case, I think we were given a capacitive system, that is simply 1/0.5s. So yes, I think I will give you around 5 minutes to solve this question, and then we can try solving it. So right now it is around 20:05. We can discuss the solution in 5 minutes. Meanwhile, if you have any doubt, you can straight away ask me. So let's try solving this question further. So the main thing is writing the transfer function of the given system. So over here the response is y and the input is the desired set point. So the transfer function will be y upon ysp. So first we will consider open loop, that is this direction. So over here we are having two plugs, that is gc and gp. So we will be taking the product of that is gc into gp, and the denominator will be having this closed loop. So that will be 1 plus gc gp. So it will become 0.2 1 plus 1 upon 0.5 s 10 upon s plus 1 2s plus 1 upon the closed loop transfer function, that is 1 plus gol. So it will become basically this entire term will come over here. So let's just simplify this further, and it will become 0.2 into 10 is 2, 2 into 0.5 s is 1s, that is basically s into 0.5 s plus 1 upon 0.5 s. So basically we just simplified these three terms over here, then we will be having s plus 1 2s plus 1, and this entire term will also come in the denominator, that is s into 0.5 s plus 1 upon 0.5 s into s plus 1 2s plus 1. So we can simplify this further, and it will become 0.5 s plus 1 into s. So this denominator will get cancelled out, and we will be having 0.5 s into s plus 1 2s plus 1 plus s into 0.5 s plus 1. Again we need to simplify this further. So you can just open the bracket. So right now I simply have the straight away the transfer function. I will just write it down for you. So let me just repeat it over here. So y upon ysp will become 0.5 s plus 1 into s upon 0.5 s plus 1 to s plus 1 into s into 0.5 s plus 1. Now let's just revisit the question. So over here we have given that for a unit step change in the set point, the change in the value of response is dash. So I don't think we need to convert this into time domain. What we have been asked is at t tends to 0, what is the value of y, and we have been given for the step change, that is ysp equal to 1 by s. So we can straight away use the final value theorem, that is we can put s tends to infinity in sys and then find the initial value of the system when the step change has been introduced. That is, we can also write it as limit s tends to infinity. So this will come over here. So it will become, so over here first is this s into corresponding to this ysp, we are having 1 upon s, then 0.5 s plus 1 into s upon, we will be having 0.5 s plus 1 2 s plus 1 plus s into 0.5s plus 1. Okay, so in this we need to put the value of infinity, so for that let's simplify this further. So since the numerator will be having a term of s square, what we need to do is we need to cancel it out by taking out s square common from the denominator, both the side, that is s square 0.5s plus 1 upon s square. Am I doing it correct? No, I am not doing it correct. So it will become this. So I'll just take s from this term common. Similarly, in denominator, we can take s square common. So it will become 0.5 s 1 by s upon 2s plus 1 plus s, simply getting common 0.5 plus 1 upon s. So this will get cancelled out. And ultimately we need to put the value of, I think, so wait a minute, let me just, okay, so we don't have to find the value at any, when the step as t tends to 0, we have to find the response at steady state value, that is what, when t tends to infinity, and s tends to 0. So that is, we need to put s equal to 0. So correspondingly we don't need to take this s square common from this denominator, so we can just put the value of s tends to 0 over here in this term. That is, but again we can see that this term s is getting cancelled out, so it is present over in this all the terms, so that will get cancelled out. That is, we will be having 0.5 into 0 plus 1 upon, over here we are having 0.5 then 1 into 1 plus 0.5 into 0 plus 1. So this will become 1 upon 1.5. So this will be our steady state value. But I don't think this is the final answer. I think algebraically I am doing something incorrect. So you can just try working out the mathematics behind this. So over here I might have done something wrong. So what I need to do is, in this s is getting cancelled out and I am putting the value of s as 0. That is 2s plus 1 over here is incorrect. So if you find the value, if you find the error, then you can just write it in chat box and I will see. There is a mathematical error. 1 by 2, so it will become s plus 2. Wait a minute. Yes, so you can try working out the solution, and I think we can just take a look on the solution that I am having over here. So yes, what we did was we calculated the transfer function of this system. So this I am writing it as 2 into 0.5 s. So this I am writing it as 2 by s. So s plus 2 by s. Okay. So yes, so we can, the final value that we are getting, I am getting from the actual solution is around 1. So the steady state value after the step change is 1. So in this question we specifically looked what that correspond, so basically how to use this block diagram representation to find the transfer function, and then using that we found the final value of the system. So now let's try solving questions related to this root stability criteria, if we are having it over here. So I think we have this question related to the stability of the process. So let's just try solving this. This is question number 11. Question number 11, but question number 3 for the day. Question number 3. So the question, we have been given that a process with a transfer function Gp is equal to 2 upon s minus 1 is controlled by a feedback proportional controller with a gain of Kc. If the transfer function of all the other elements in the closed loop in the control loop are unity, then which of the following conditions produces a stable closed loop response? So first we need to draw a block diagram representation of this system and then find the transfer function model, and then use the rules that we studied in today's class in order to find the range of the Kc. So I'll just, right now it is around 2024. We will discuss the solution at around 2030. So you can try solving this in 6 minutes. So I will just draw the block diagram for you. However, I don't think you need such a detailed block diagram in this question. So let's just start it step by step. So we are having this process GP is equal to 2s minus 1. Corresponding to that, we will be getting a response, that is y. In order to control this, what I will do is I will just feed back again to the system. Is I need to measure the response using a measuring element or a sensor with a transfer function of gm, and in this question we have been given that all the control loop elements are 1. So I will write it as 1. Then I will just feed back the system, but I will also having a set point that I will be comparing. There will be having an error, so that error I will be feeding back to the controller. So controller will be having a transfer function of gc. This is also equal to 1. Then I will be having a final control element, that is a control valve. It will also have the transfer function of 1, and then that is what we will be feeding to the system. So you need to write the transfer function model for this block diagram representation, and then use the rules of stability. So what we studied was we have to find the roots of characteristic equation, and so this will give us poles of the system. So if the poles of the system lies on this half of the plane, that implies the system is stable. So that using this you can find the solution. So I will just try solving it in 3 minutes. This is a very simple question. You can try doing it in 3 minutes. So yes, let's try solving the question. So I have drawn the block diagram. So first we need to write the transfer function of the model. So that is basically y upon ysp is equal to open loop transfer function upon 1 plus GCL. So this will be the product of these three terms, and the denominator will be the product of all the terms. However, this is known as characteristic equation. Characteristics equation, and we need to find the roots of the denominator. So we will simply find the roots of the denominator, that is basically the poles of the system. So it will become 1 plus the product of all the GC, GV and GM is 1, and then we are having 2 into S minus 1. But I think for controller we are having proportional controller has a gain of Kc. That is, over here we are having GCS Kc. So that will become 2 Kc upon S minus 1. So this is my characteristic equation, and this should be equal to 0. I will simplify this further in order to find the roots to give poles of the system. That is basically 2 Kc plus S minus 1 is equal to 0. Now for this system to be stable, we studied that roots should lie on this half of the plane. That is, S should be less than 0. For that to happen, we can say that the value of S over here is 1 minus two Kc. Am I doing it correct? S equal to minus 1 minus 2 Kc. So this should be less than 0. That is 1 upon 2 Kc should be greater than 0. That gives us minus 1 by 2 upon Kc. That is, value of Kc should be greater than 1 upon 2. I think I'm doing something incorrect over here. So 1 plus 2 Kc upon S minus 1, that is S minus 1 upon 2 Kc. Okay, over here I'm having S minus 1. That is, S is equal to 1 minus 2 Kc. Okay, that means correct it. The value of Kc should not have been negative. That is where I get to know that I'm doing something incorrect. So this is 1 minus 2 Kc less than 0. This will give me 1 is less than 2 Kc. So over here we are getting the value of Kc should be greater than 1/2. So for the system to be stable, we studied that the value of Kc should be greater than 0.5, that is 1/2. Sorry. So this is our final answer. So from the given option, we can select option D as the correct option. Now let's solve question related to root array, and then we can solve few more complex problems. So this is a fairly simple question whereby we haven't been given block diagram also, so we can try solving this. So I'll just copy paste the question. So in this question, you will be requiring the root array. So I am straight away providing that also. But you need to remember the root array for your exam purposes, and it is fairly straightforward to remember also. But over here, where are my notes? So yes, so in this question we have been given the characteristic equation given by this equation, and we have to find the range of k beyond which the system becomes unstable. So one way to find the value of k is to find the roots of this equation. So since this is a third order polynomial, we will be having 3 roots which will all be function of kc, s1, s2, s3, and then analyzing all those 3 roots we can find the range of kc. Or else what we can do is we can use the root array, which will give us whereby we don't need to manually calculate the roots, and we can find the range of kc. So right now it is around 20:37. I will discuss the solution in around 8 minutes at 20:45. Let's say this is a simple question, so I will just give you 5, let's say around 3 minutes, 20:40. So solve in 3 minutes, and then we will, after solving this question, we will look on to the another question also. So try solving it. So let's try solving this question. So yes. So we have been given this characteristic equation. So one way to analyze the stability is by finding the roots. The another way is by using the root array. However, in this question, there will be multiple roots which will be a function of k, and finding that we don't have some straightforward formula to calculate the roots. That is why we are using a root array. So first we will let's just fill the value of all the elements in this table itself. So the equation that we have been provided is 6s cube plus 11s square plus 6s and 1 plus k is equal to 0. So that is basically a0, a1, a2, a3. So 6, 11, 6, 1 plus k. If I am going incorrect, just mention me. Then we need to find the value of a1, and I think rest all terms we can find the value of a1. Since we are having these two values, we need to find the value of a1, a2. Rest all terms will be straight away 0. So basically this all the terms will be 0. We will be only having this diagonal over here. So we will be finding the value of a1, that is a1 into a2, 66 minus 6 into 1 plus k upon a1 is 11. Similarly, am I doing it correct? So we can simplify this further, that is 66 minus 6 is 60 minus of 6k upon 11 value of a1. Then we are having the value of a2. So since all these terms a4, a5 are 0, this term will become 0. Similarly, if we take a look on this term, so a2 is 0, so this term becomes 0, a1 get cancelled out, and this will be, so b1 will be basically a2 is 0, a1 is some value, a1, so a3 is basically 1 plus k. And we studied from the criteria that, see, a0 was already positive, then each of these terms are positive. That means we need to look into this fourth array. So all these terms needs to be positive. So 6 and 11 are already positive. So this term should be greater than 0, as well as 1 plus k should also be greater than 0. So using this, we can write that 60 minus 6k should be greater than 0, or k should be greater than minus of 1. So this will give us 60 should be, okay, so value of k should be less than 10. Hope I am doing correct. So over here we can see that the system is stable when the value of k is between this term minus 1 to k. So this is the range on which the system will be stable. Now if we look on the options given in the question, so what was the question that we were solving? Okay. So over here we have been asked to find the critical condition for stability of the PI feedback control system. That is, the system will be critically stable when we need to equate it to 0. That is, this term should be equal to 0, that is 60 minus 6k should be equal to 0. So this will give us k is equal to 10. So since we have been asked to find the critically stable value, we will write the value of k as 10. I hope that is clear to you. So the final answer over here, No, so the question was system just becomes unstable. So in that case also, using this range, the system will become stable at the boundary points. However, we will select this value because that will satisfy both of these criteria. That is why we selected the value of k equal to 10. So this question related critical condition of stability was for the next question. So we will try solving this question also. So this is question number, last question for the day, whereby we have been given a PI controller with integral time constant 0.1 is to be designed to control a process with transfer function given by this equation. Assume the transfer function of the measuring element and the final control element are both unity. The gain of the controller that will constitute the critical condition for stability of the PI feedback control system is dash. So again, I will just share the methodology. So this is the question we have been given, whereby we have been given the process model or the transfer function of the process, and then we have been given a PI controller. So we have to first draw a block diagram representation, write the transfer function model, and then comment on the stability of the system. So over here also you will be needing the root array. So I'm just copy pasting it. Okay, so you can try solving this question. We will discuss it in a couple of minutes. That's around 3 minutes. At around 8:50, we can try solving it. This is again very similar to the previous question, but over here we have been given a fairly complex system of the PI controller and the second order process. That is the only difference, whereas the solution methodology will remain the same. So let's just try solving the question. I will show the root array later on. So first we will draw the block diagram of the question. That is, we have been given a PI controller with an integral time constant 1 and the process. Rest all things are 1. So rather than drawing the block diagram, we can straight away write the characteristic equation as 1 plus product of all the block diagram, that is GC, GB, GM, GP. Now for the PI controller, we need to write the transfer function model. So for PI controller, we are having the transfer function as C of S upon E of S can be written as Kc into 1 plus 1 upon tau I into S. So this transfer function model we need to use. So we can write this over here. So it will become Kc into 1 plus 1 upon tau is. This is GB rest all things over, and then we are having the process. The process is 10 upon s square plus 2s plus 100. S square plus 2s plus 100. So using this we will be getting a polynomial in S, and then we will be using the root array. But we have been also provided the value of integral time, that is tau I is 0.1. And the value of Kc we have to find. So this will become Kc into 1 plus 1 upon 0.1 S into 10 upon S square plus 2S plus 100. So simplifying this, we just need to find the roots of this equation. So basically we can neglect the denominator once we have simplified this. So it will become 0.1 S into S square plus 2S plus 100 plus Kc into 0.1 S plus 1 into 10. So this should be, this all these things should be equal to 0 for the characteristic equation to be true. So and that implies 0.1 S cube. Let's just take the 0.1 as common. Basically, let's just divide the equation by 0.1. So that will become 100 over here. So the characteristic equation will become S cube plus 2s square plus 100s plus, am I doing it correct? Yes, plus 100 Kc into 0.1 into S. So that is basically 10 Kcs plus 100 times Kc equal to 0. So this is our characteristic equation. So we can write this also as S cube plus 2s square plus 100 plus 10 Kc into S plus 100 Kc equal to 0. So once we have this equation, we can calculate the values of the root array. So over here the value of A0 is 1, A1 equal to 1, A2 equal to 100 plus 10 Kc, A3 equal to 100. So we are having this 4 value. We will calculate the value of A1, that is A1, A2. Simply 100 plus 10 Kc minus of A0, A3 minus of 100 upon A1. A1 is 1. So over here A1 is 2. That is where I am incorrect. So A1, A2 will become, on the denominator it will be 2. So 200 into 20C. So basically this will give me 100 plus 20 Kc upon 2. You can just try verifying that whether I'm doing it algebraically correct or not. I think there is some mistake. Over here also we are having the value of Kc. So A0 into A3 will become 100 Kc. So the value of A1 becomes not 200, it is 100. 100 minus of 80 kc by 2. Now since we had to find the value of at that for the critical stability, we can just equate this as 0. So that will give us the value of kc as 100 upon 8. Again I am doing something incorrect. A1, A2, that is 200 plus 20 kc minus A0, A3. A0, A3 is 100 kc upon A1. A1 is 2. So all these things are correct. So the value of kc should be 200 upon 80, that is 2.5. This is correct. We can also find the other elements over here. So since A5 is 0, this will become 0. So this will be simply A4. So this B1 will become A1, A3 minus of A1, A4 upon A1. Now value of A4 is 0. So this will simply become A3. So here we don't need to analyze anything. That is, we will be only getting the value of Kc as 2.5. That is, we can write the value of Kc for this PI feedback control system as 2.5. So you need to be mathematically accurate in order to find this solution. So once you are mathematically accurate, you just need to use this table and do some calculation in order to comment on the stability. So I hope this much is clear. So we solved questions related to root array and this direct substitution method and this block diagram representation in today's class. If you have any doubt, you can just ask, or else you can end today's lecture. I don't think anyone is attending. So I think we can end today's class. So in the next class, we will first just briefly cover the topics related to this both stability criterion, that's frequency response, and then try with the content of week 6 and try to cover up the backlog of this class also. So okay, thank you for joining. We can end today's class.